Part 1 of Chapter 3 of A Popular History of Astronomy during the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melanie T. A Popular History of Astronomy during the 19th Century by Agnes Mary Clerke. Chapter 3. Recent solar eclipses. By observations made during a series of 5 remarkable eclipses, comprised within a period of 11 years, knowledge of the solar surroundings was advanced nearly to its present stage. Each of these events brought with it a fresh disclosure of a definite and unmistakable character. We will now briefly review this orderly sequence of discovery. Photography was first systematically applied to solve the problems presented by the eclipsed sun, July 18, 1860. It is true that a daguerreotype taken by Bowalski with the Königsberg heliometer during the eclipse of 1851 is still valuable as a record of the corona of that year, and some subsequent attempts were made to register partial phases of solar occultation, notably by Professor Bartlett at West Point in 1854. But the ground remained practically unbroken until 1860. In that year the track of totality crossed Spain, and Tiver accordingly. Warren de la Rue transported his photoheliograph, and Father Secchi his 6-inch Cauchoix refractor. The question then primarily at issue was that relating to the nature of the red protuberances, although, as already stated, the evidence collected in 1851 gave a reasonable certainty of their connection with the sun. Objectors were not silenced, and when the side of incredulity was supported by so considerable an authority as Monsieur Fay, it was impossible to treat it with contempt. 2 crucial tests were available. If it could be shown that the fantastic shapes suspended above the edge of the dark moon were seen under an identical aspect from 2 distant stations, that fact alone would annihilate the theory of optical illusion or mirage, while the certainty that they were progressively concealed by the advancing moon on one side and uncovered on the other would effectually detach them from dependence on our satellite and establish them as solar appendages. Now both these tests were eminently capable of being applied by photography, but the difficulty arose that nothing was known as to the chemical power of the rosy prominence light, while everything depended on its right estimation. A shot had to be fired, as it were, in the dark. It was a matter of some surprise and of no small congratulation that, in both cases, the shot took effect. De la Rue occupied a station at River Bellosa, in the upper Ebro Valley. Secchi set up his instrument at Desierto de las Palmas, about 250 miles to the southeast, overlooking the Mediterranean. From the totally eclipsed sun, with its strange garland of flames, each observer derived several perfectly successful impressions, which were found, on comparison, to agree in the most minute details. This at once settled the fundamental question as to the substantial reality of these objects, while their solar character was demonstrated by the passage of the moon in front of them, indisputably attested by pictures taken at successive stages of the eclipse. That forms seeming to defy all laws of equilibrium were, nevertheless, not wholly evanescent, appeared from their identity at an interval of 7 minutes, during which the lunar shadow was in transit from one station to the other, and the singular energy of their actinic rays was shown by the record on the sensitive plates of some prominences invisible to the telescope. Moreover, photographic evidence strongly confirmed the inference, previously drawn by Grant and others, and now with fuller assurance by Secchi, that an uninterrupted stratum of prominence matter encompasses the Sun on all sides, forming a reservoir from which gigantic jets issue, and into which they subside. Thus, first fruits of accurate knowledge regarding the solar surroundings were gathered, while the value of the brief moments of eclipse gained indefinite increase, by supplementing transient visual impressions with the faithful and lasting records of the camera. In the year 1868 the history of eclipse spectroscopy virtually began, as that of eclipse photography in 1860. That is to say, the respective methods then first gave definite results. On the 18th of August 1868 the Indian and Malayan peninsulas were traversed by a lunar shadow producing total obscuration during 5 minutes and 38 seconds. 2 English and 2 French expeditions were dispatched to the distant regions favoured by an event so propitious to the advance of knowledge, chiefly to obtain the verdict of the prism as to the composition of the prominences. Nor were they dispatched in vain. An identical discovery was made by nearly all the observers. At Jamkhandi, in the Western Ghauts, where Lieutenant, now Colonel, Herschel was posted, unremitting bad weather threatened to baffle his eager expectations. But during the lapse of the critical 5½ minutes the clouds broke, and across the driving rack a long finger-like projection jutted out over the margin of the dark lunar globe. In another moment the spectroscope was pointed towards it. 3 bright lines, red, orange, and blue, flashed out, and the problem was solved. The problem was solved in the general sense that the composition out of glowing vapours of the objects infelicitously termed protuberances or prominences was no longer doubtful, although further inquiry was needed for the determination of the particular species to which those vapours belonged. Similar but more complete observations were made with less atmospheric hindrance by Tennant and Janssen at Guntur, by Pogson at Masulipatam, and by Rayet at Warton on the coast of the Malay Peninsula, the last observer counting as many as 9 bright lines. Among them it was not difficult to recognise the characteristic light of hydrogen, and it was generally, though over hastily, assumed that the orange ray matched the luminous emissions of sodium. But fuller opportunities were at hand. The eclipse of 1868 is chiefly memorable for having taught astronomers to do without eclipses, so far at least as one particular branch of solar inquiry is concerned. Inspired by the beauty and brilliancy of the various tinted prominence lines revealed to him by the spectroscope, Janssen exclaimed to those about him, "Je verrai ces longueurs-là en dehors des éclipses." On the following morning he carried into execution the plan which formed itself in his brain while the phenomenon which suggested it was still before his eyes. It rests upon an easily intelligible principle. The glare of our own atmosphere alone hides the appendages of the sun from our daily view. To a spectator on an airless planet, the central globe would appear attended by all its splendid retinue of crimson prominences, silvery corona, and far-spreading zodiacal light projected on the star-spangled black background of an absolutely unilluminated sky. Now, the spectroscope offers the means of indefinitely weakening atmospheric glare by diffusing a constant amount of it over an area widened ad libitum. But monochromatic or bright line light is, by its nature, incapable of being so diffused. It can, of course, be deviated by refraction to any extent desired, but it always remains equally concentrated in whatever direction it may be thrown. Hence, when it is mixed up with continuous light, as in the case of the solar flames shining through our atmosphere, it derives a relative gain in intensity from every addition to the dispersive power of the spectroscope with which the heterogeneous mass of beams is analysed. Employ prisms enough, and eventually the undiminished rays of persistent colour will stand out from the continually fading rainbow-tinted band, by which they were at first effectually veiled. This Janssen saw by a flash of intuition while the eclipse was in progress, and this he realised at 10 a.m. the next morning, August 19th, 1868, the date of the beginning of spectroscopic work at the margin of the unobscured sun. During the whole of that day, and many subsequent ones, he enjoyed, as he said, the advantage of a prolonged eclipse. The intense interest with which he surveyed the region suddenly laid bare to his scrutiny was heightened by evidences of rapid and violent change. On the 18th of August, during the eclipse, a vast spiral structure, at least 89,000 miles high, was perceived planted in a surprising splendour on the rim of the interposed moon. If was formed, as General Tennant judged from its appearance in his photographs, by the encounter of two mounting torrents of flame, and was distinguished as the Great Horn. Next day it was in ruins, hardly a trace remained to show where it had been. Janssen's spectroscope furnished him besides with the strongest confirmation of what had already been reported by telescope and the camera as to the continuous nature of the Scarlet Sierra lying at the base of the prominences. Everywhere at the sun's edge the same bright lines appeared. It was not until the 19th of September that Janssen thought fit to send news of his discovery to Europe. It seemed little likely to be anticipated, yet a few minutes before his dispatch was handed to the Secretary of the Paris Academy of Sciences, a communication similar in purport had been received from Sir Norman Lockyer. There was no need to discuss the narrow and wearisome question of priority. Each of the competitors deserves and has obtained full credit for his invention. With noteworthy and confident prescience, Lockyer, in 1866, before anything was yet known regarding the constitution of the red flames, ordered a strongly dispersive spectroscope for the express purpose of viewing, apart from eclipses, the bright line spectrum which he expected them to give. Various delays, however, supervened, and the instrument was not in his hands until October 16, 1868. On the 20th he picked up the vivid rays, of which the presence and approximately the positions had in the interim become known. But there was little doubt that, even without the previous knowledge, they would have been found, and that the eclipse of August 18th only accelerated a discovery already assured. Sir William Huggins, meanwhile, had been tending towards the same goal during 2.5 years in his observatory at Tulse Hill. The principle of the spectroscopic visibility of prominence lines at the edge of an uneclipsed sun was quite explicitly stated by him in February 1868, and he devised various apparatus for bringing them into actual view, but not until he knew where to look did he succeed in seeing them. Astronomers, thus liberated by the acquisition of power to survey them at any time, from the necessity of studying prominences during eclipses, were able to concentrate the whole of their attention on the corona. The first thing to be done was to ascertain the character of its spectrum. This was seen in 1868 only as a faintly continuous one, for Rayet, who seems to have perceived its distinctive bright line far from the summits of the flames, connected it nevertheless with those objects. On the other hand, Lieutenant Campbell ascertained on the same occasion the polarization of the coronal light in planes passing through the sun's centre, thereby showing that light to be, in whole or in part, reflected sunshine. But if reflected sunshine, it was objected, the chief at least of the dark Fraunhofer lines should be visible in it, as they are visible in moonbeams, sky illumination, and all other sun-derived light. The objection was well founded, but it was prematurely urged, as we shall see. On the 7th of August 1869, a track of total eclipse crossed the continent of North America diagonally, entering at Bering Straits and issuing on the coast of North Carolina. It was beset with observers, but the most effective work was done in Iowa. At Des Moines, Professor Harkness of the Naval Observatory, Washington, obtained from the corona an absolutely continuous spectrum, slightly less bright than that of a full moon, but traversed by a single green ray. The same green ray was seen at Burlington and its position measured by Professor Young of Dartmouth College. It appeared to coincide with that of a dark line of iron in the solar spectrum, numbered 1474 on Kirchhoff's scale. But in 1876 Young was able, by the use of a greatly increased dispersion, to resolve the Fraunhofer line 1474 into a pair, and the more refrangible member of which he considered to be the reversal of the green coronal ray. Scarcely called in question for over 20 years, the identification nevertheless broke down through the testimony of the eclipse photographs of 1898. Sir Norman Lockyer derived from them a position for the line in question notably higher up the spectrum than that previously assigned to it. Instead of 5317, its true wavelength proved to be 5303 10/millionths of a millimetre. Nor does it make any show by absorption in dispersed sunlight. The originating substance, designated coronium, of which nothing is known to terrestrial chemistry, continues luminous, at least 300,000 miles above the sun's surface, and is hence presumably much lighter even than hydrogen. A further trophy was carried off by American skill 16 months after the determination due to it of the distinctive spectrum of the corona. The eclipse of December 22nd, 1870, though lasting only 2 minutes and 10 seconds, drew observers from the New as well as from the Old World to the shores of the Mediterranean. Janssen issued from beleaguered Paris in a balloon, carrying with him the vital parts of a reflector specially constructed to collect evidence about the corona. But he reached Oran only to find himself shut behind a cloud curtain more impervious than the Prussian lines. Everywhere the sky was more or less overcast. Lockyer's journey from England to Sicily and shipwreck in the Psyche were recompensed with a glimpse of the solar aureola during 1 second and a half. 3 parties stationed at various heights on Mount Etna saw absolutely nothing. Nevertheless, important information was snatched in despite of the elements. The prominent event was Young's discovery of the reversing layer. As the surveying solar crescent narrowed before the encroaching moon, the dark lines of the spectrum, he tells us, and the spectrum itself gradually faded away, until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was filled with bright lines more numerous than one could count. The phenomenon was so sudden, so unexpected, and so wonderfully beautiful, as to force an involuntary exclamation. Its duration was about 2 seconds, and the impression produced was that of a complete reversal of the Fraunhofer spectrum, that is, the substitution of a bright for every dark line. Now something of the kind was theoretically necessary to account for the dusky rays in sunlight which have taught us so much, and have yet much more to teach us, so that, although surprising from its transitory splendour, the appearance could not be strictly called unexpected. Moreover, its premonitory symptom in the fading out of these rays had been actually described by Secchi in 1868, and looked for by Young as the moon covered the sun in August 1869. But with the slit of his spectroscope placed normally to the sun's limb, The bright lines gave a flash too thin to catch the eye. In 1870 the position of the slit was tangential. It ran along the shallow bed of incandescent vapours instead of cutting across it. Hence his success. The same observation was made at Xeres de la Frontera by Mr. Pye, a member of Young's party, and although an exceedingly delicate one, has since frequently been repeated. The whole Fraunhofer series appeared bright, omitting other instances, to Maclear, Herschel and Fries in 1871, at the beginning or end of totality, to Pogson at the break-up of an annual eclipse, June 6, 1872, to Stone at Klipfontein, April 16, 1874, when he saw the field full of bright lines. But between the picture presented by the veritable Plus de Ligne Brillante, which descended into Monsieur Trépier's spectroscope for 3 seconds after the disappearance of the sun, May 17, 1882, and the familiar one of the dark line solar spectrum, certain differences were perceiving, showing their relation to be not simply that of a positive or negative impression. A reversing layer, or stratum of mixed vapours, glowing but at a lower temperature than that of the actual solar surface, was an integral part of Kirchhoff's theory of the production of the Fraunhofer lines. Here it was assumed that the missing rays were stopped, and here also it was assumed that the missing rays would be seen bright, could they be isolated from the overpowering splendour of their background. This isolation is effected by eclipses, with the result, beautiful confirmatory of theory, of reversing or turning from dark to bright the Fraunhofer spectrum. The completeness and precision of the reversal, however, could not be visually attested, and a quarter of a century elapsed before a successful snapshot provided photographic evidence on the subject. It was taken at Novaya Zemlya by Mr. Shackleton, a member of the late Sir George Baldwin-Power's expedition to observe the eclipse of August 9, 1896, and similar records in abundance were secured during the Indian eclipse of January 22, 1898, and the Spanish-American eclipse of May 28, 1900. The result of their leisurely examination has been to verify the existence of a reversing layer, in the literal sense of the term. It is true that no single flash photograph is an inverted transcript of the Fraunhofer spectrum. The lines are, indeed, in each case, speaking broadly, the same, but their relative intensities are widely different. Yet this need not occasion no surprise when we remember that Fraunhofer spectrum integrates the absorption of a multitudinous strata, various in density and composition, while only the upper section of the formation comes within view of the sensitive plates exposed at totalities, the lie-lowing vaporous beds being necessarily covered by the moon. The total depth of this glowing envelope may be estimated at 500 to 600 miles, and its normal state seems to be one of profound tranquillity, judging from the imperturbable aspect of the array of dark lines due to its sifting action upon life. The last of the 5 eclipses, which we have grouped together for separate consideration, was visible in southern India and Australia, December 12, 1871. Some splendid photographs were secured by the English parties on the Malabar coast, showing for the first time the remarkable branching forms of the coronal emanations. But the most conspicuous result was Janssen's detection of some of the dark Fraunhofer lines, long vainly sought in the continuous spectrum of the corona. Chief among these was the D line of sodium, the original index, it might be said, to solar chemistry. No proof could be afforded more decisive than this faint echoing back of the distinctive notes of the Fraunhofer spectrum, that the polariscope had spoken the truth in asserting a large part of the coronal radiance to be reflected sunlight. but it is usually so drenched in original luminosity that its special features are almost obliterated. Janssen's success in seizing them was due in part to the extreme purity of the air at Scholer in the Nile Heres, where he was stationed, in part to the use of an instrument adapted by its large aperture and short focus to give an image of the utmost brilliancy. His observation, repeated during the Caroline Island eclipse of 1883, was photographically verified 10 years later by Monsieur de la Borne Pluvinel in Senegal. An instrument of great value for particular purposes was introduced into eclipse work in 1871. The slitless spectroscope consists simply of a prism placed outside the object glass of a telescope or the lens of a camera, whereby the radiance encompassing the eclipsed sun is separated into as many differently tinted rings as it contains different kinds of light. These tinted rings were simultaneously viewed by Respighi at Puda-Kota and by Lockyer at Baikal. Their photographic registration by the latter in 1875 initiated the transformation of the slitless spectroscope into the prismatic camera. Meanwhile, the use of an ordinary spectroscope by Herschel and Tennant at Dodder Beta showed the green ray coronium to be just as bright in a rift in the adjacent streamer. The visible structure of the corona was thus seen to be independent of the distribution of the gases which enter into its composition. By means, then, of the 5 great eclipses of 1860 to 1871, it was ascertained, first, that the prominences, and at least the lower part of the corona, are genuine solar appurtenances. Secondly, that the prominences are composed of hydrogen and other gases in a state of incandescence, and rise, as irregular outliers, from a continuous envelope of the same materials, some thousands of miles in thickness. And thirdly, that the corona is of a highly complex constitution, being made up in part of glowing vapours, in part of matter capable of reflecting sunlight. We may now proceed to consider the results of subsequent eclipses. These have raised, and have helped to solve, some very curious questions. Indeed, every carefully watched total eclipse of the sun stimulates as well as appeases curiosity, and leaves a legacy of outstanding doubt, continually, as time and inquiry go on, removed, but continually replaced. It cannot be denied that the corona is a perplexing phenomenon, and that it does not become less perplexing as we know more about it. It has presented itself under quite a new and strange aspect. on the occasion of the eclipse which visited the western states of North America on July 29, 1878. The conditions of observation were peculiarly favourable. The weather was superb. Above the Rocky Mountains the sky was of such purity as to permit the detection of Jupiter's satellites with the naked eye on several successive nights. The opportunity for advancing knowledge was made the most of. Nearly 100 astronomers, including several Englishmen, occupied 12 separate posts, and prepared for an attack in force. The question had often suggested itself, and was a natural one to ask, whether the corona sympathizes with the general condition of the sun, whether, either in shape or brilliancy, it varies with the progress of the sunspot period. A more propitious moment for getting this question answered could hardly have been chosen than that at which the eclipse occurred. Solar disturbance was just then at its lowest ebb. The development of spots for the month of July 1878 was represented on Wolf's system of relative numbers by the fraction 0.1, as against 135.4 for December 1870, an epoch of maximum activity. The chromosphere was, for the most part, shallow and quiescent. Its depth above the spot zones had sunk from about 6,000 to 2,000 miles. Prominences were few and faint. Obviously, if a type of corona corresponding to a minimum of sunspots existed, it should be seen then or never. It was seen, But while in some respects it agreed with anticipation, in others it completely set it at naught. The corona of 1878, as compared with those of 1869, 1870, and 1871, was generally admitted to be shrunken in its main outlines and much reduced in brilliancy. Lockyer pronounced it 10 times fainter than 1871. Harkness estimated its light at less than 1/7 that derived from the mist-blotted aureola of 1870. In shape, too, it was markedly different. When the sunspots are numerous, the corona appears to be most fully developed above the spot zones, thus offering to our eyes a rudely quadrilateral contour. The 4 great luminous sheaves forming the corners of the square are made up of rays curving together from each side into a synclinal or ogival groups, each of which may be compared to the petal of a flower. To Janssen in 1871, the eclipsing moon seemed like the dark heart of a gigantic dahlia, painted in light on the sky, and the similitude to the ornament on the compass card used by Airy in 1851 well conveys the decorative effect of the beamy radiated kind of aureola. Never, it would appear, absent when solar activity is at a tolerably high pitch. In his splendid volume on eclipses, with which the systematic study of coronal structure may be said to have begun, Mr. Ranyard first generalized the synclinal peculiarity by a comparison of records, but the symmetry of the arrangement, though frequently striking, is liable to be confused by secondary formations. He further pointed out, with the help of careful drawings from the photographs of 1871 made by Mr. Wesley, the curved and branching shapes assumed by the component filaments of massive bundles of rays. Nothing of all this, however, was visible in 1878. Instead, there was seen, as the groundwork of the corona, a ring of pearly light, nebulous to the eye, but shown by telescopes and in photographs to have a fibrous texture, as if made up of the tufts of fine hair. North and south, a series of short, vivid, electrical-looking flame brushes diverged with conspicuous regularity from each of the solar poles. Their direction was not towards the centre of the sun, but towards each summit of his axis, so that the farther rays on each side started almost tangentially to the surface. By the leading and a truly amazing characteristic of the phenomenon was formed by 2 vast, faintly luminous wings of light expanded on either side of the sun in the direction of the ecliptic. These were missed by very few careful onlookers, but the extent assigned to them varied with skill in and facilities for seeing. By far the most striking observations were made by Newcomb at Separation, Wyoming, and by Cleveland Abbey on the shoulder of Pike's Peak, and by Langley at its summit, an elevation 14,100 feet above the sea. Never before had an eclipse been viewed from anything approaching that altitude, or under so translucent a sky. A proof of the great reduction in the atmospheric glare was afforded by the perceptibility of the corona 4 minutes after totality was over. For the 165 seconds of its duration, the remarkable streamers above alluded to continued, persistently visible, stretching away right and left of the sun to a distance of at least 10 million miles. One branch was traced over an apparent extent of fully 12 lunar diameters, without a sign of definite termination having been reached, and there was no grounds for supposing the other more restricted. The resemblance to the zodiacal light was striking, and a community of origin between that enigmatical member of our system and the corona was irresistibly suggested. We should indeed expect to see, under such exceptionally favourable atmospheric conditions as Professor Langley enjoyed on Pike's Peak, the roots of the zodiacal light presenting near the sun just such an appearance as he witnessed. But we can imagine no reason why their visibility should be associated with a low state of solar activity. Nevertheless, this seems to be the case with the streamers which astonished astronomers in 1878. For in 1867, when similar equatorial emanations, accompanied by similar symptoms of polar excitement, were described and depicted by Grosch, of the Santiago Observatory, sunspots were at a minimum, while the corona of 1715, which appears from the record of it by Roger Coates to have been of the same type, preceded by 3 years the ensuing maximum. The eclipsed sun was seen by him at Cambridge, May 2nd, 1715, encompassed with a ring of light about 1/6 of the moon's diameter in breadth, upon which it was superposed a luminous cross formed of long bright branches lying very nearly in the plane of the ecliptic, and shorter polar arms so faint as to be only intermittently visible. The resemblance between his sketch and Cleveland Abbe's drawing of the corona of 1878 is extremely striking. It should nevertheless be noted that some conspicuous spots were visible on the sun's disk at the time of Coates' eclipse, and that the preceding minimum, according to Wolf, occurred in 1712. Thus the coincidence of the epochs is imperfect. Professor Cleveland Abbe was fully persuaded that the long rays carefully observed by him from Pike's Peak were nothing else than streams of meteorites rushing towards or from perihelion, and it is quite certain that the solar neighbourhood must be crowded with such bodies. But the peculiar structure at the base of the streamers displayed in the photographs, the curved rays meeting in pointed arches like Gothic windows, the visible upspringing tendency, the filamentous texture, speak unmistakably of the action of forces proceeding from the sun, not of extraneous matter circling round him. A further proof in the sympathetic change in the corona is afforded by analysis of its light. In 1878, the bright lines so conspicuous in the coronal spectrum in 1870 and 1871 had faded to the very limit of visibility. Several skilled observers failed to see it at all, but Young and Eastman succeeded in tracing the green coronium ray all around the sun, to a height estimated at 340,000 miles. The substance emitting it was thus present, though in a low state of incandescence. The continuous spectrum was relatively strong. Faint traces of the Fraunhofer lines attested for it an origin. In part by reflection, and polarization was undoubted, increasing towards the limb, whereas in 1870 it reached a maximum at considerable distance from it. Experiments with Edison's tassometer seem to show that the corona radiates a sensible amount of heat. End of Part 1 of Chapter 3.